Fritz is on the first.
That brand new plane she's standing in front of.
Yeah, and I don't remember seeing that student here.
That's, looks like a newer model 182 right there.
Oh, the airplane.
Yeah, it's got a craptastic thing that's got a hanger.
She said, sweet.
Okay, so Tuesday, they're gonna ask you all three subatomics. Freak out. Proton, neutron, electron. What factor determines if a material makes a suitable semiconductor? That's the same answer. It's the number of electrons in the valence shell. Fewer electrons is a better conductor. More electrons in the valence shell is a better insulator. And then a semiconductor, there's no line where something becomes one and the other. So a semiconductor.
Fewer electrons is a better.
The answer is what determines if a material makes anything is it literally boils down to the number of electrons in the valence shell. You can simply say that.
Okay, but fewer electrons.
Fewer electrons makes a better conductor.
More is less, less is best.
What factor determines if a material makes a suitable? Oh, that's the same one. The number of electrons. Which unit of measure describes resistance? So you guys would have. Well, you guys are gonna have no trouble. Okay, remember, I still get not just one person, engineering notation. And the value it has to be 10 to the third, 10 to the sixth, 10 to the ninth, 10 to the 12th. Somebody gave me 10 to the fourth on a couple answers.
You remind us that you did.
I'll try. Were you the 10 to the fourth?
No.
I don't always look at the names. You know, I see the mistakes and I check the wrongs and I put them in a pile. And then I go back and I enter them in my sheet by the scores. I don't really ever put a name to the mistakes. But somebody gave me 10 to the fourth, like at least twice. Right? Okay, so and then metric notation, I want to see a metric value. Pico, giga, mega, something. Okay, here's an explanation. Engineering notation is similar to scientific notation, except the notation can have from 1 to 3 digits. Must have. It says can. We want 1 to 3 digits to the left of the decimal place. And powers of 10 are multiples of 3. So there's engineering okay, there's an example. 234 times 10 to the third would be 234,000. Okay, so these are the questions I asked you before. The first one is good. The second one looks good. No, is it a 6 or 5?
6.
Okay, so that one's good. The negative 4.5 times 10 to the 6th, that's good too.
They're all good.
Now the third one, or the next one, I mean. No, because I don't have I don't have a whole value to the left of the decimal. And then the last one has too many.
Maybe too many.
I want between 1 and 3 digits to the left of the decimal. That has 4 digits.
It's 6.
Are you giving a little explanation like this, or you have a
Oh, we
yes or no? It's good or it's not good?
I'm not sure I understand the question.
I mean, when we, on
Oh,
the
the
test.
explanation on this one? This is the
No.
only explanation
No,
you're
no,
gonna
no,
get. You're on your own after today.
I mean, when you're taking the test, do you want a little,
No.
I just say yes or no, it's.
No, in fact, it's not gonna ask you. This, this is just my examples. This part is not on the test. But,
Oh, it is.
no, and I apologize for that. I guess I should have clarified. What I was doing is I dropped this in to give you examples.
Oh, okay, okay.
So, yeah, no, I apologize. I fully understand. Yes. Okay, so show, that number.
Pico.
Or something similar to it in
Point
metric
zero zero
notation.
one.
Again, the key word is metric, so I wanna see pico, giga, something, centa, milli,
How many zeros are up there?
I don't know.
11 zeros.
12. Study it. I can't guarantee that's the number of zeros on the test, or that there's even gonna be a one in there. And it may not even be amps, it might be ohms.
Yeah, there's 11 zeros, one.
So, but it's gonna be similar to that. And this is not on the test either, so.
Is that a pico?
Yeah, it's 12.
That was 1 picoamp on the sensor for that one.
It's 1 P.
One P.
So we would be moving the decimal to the right bunches of times, 12 times. Did you get it? Too late? I'll try.
I get it.
It's gonna go back and forth. Okay, this is not on the test, but these were examples of metric notations. I put this in here thinking it was a good explanation, but the test will go either from the base unit out here or from out here back to the base unit. So these go from microvolts to kilovolts, so I wouldn't lose too much sleep over these. But you get an idea. What color code is, so you're gonna get a so many ohm resistor plus or minus 5 or 10%, and you just give me the colors. And it looks like it happens twice. The value and tolerance. So the tolerance is the plus or minus. If it says tolerance plus or minus 5 through 10%, it's the range is what I'm looking for when I want to either add and subtract the percentage. And there it is. What are the possible minimum maximum resistance values? That would also be where you add and subtract the percentage for the previous question. So you're going to get one of those. So you're going to get two where you've got to convert you're going to have to convert one resistor into colors and then get two colors and convert those back into numbers and then give me a range on the last one. And there's just a little reminder. Again, remember that third line is the multiplier. That's the number of zeros. The first two are just direct digits. What is the value and tolerance of a resistor color-coded red, green, red, red? And I guarantee that's not the one on the test. So that's 2, 5, 2, 5, and 2 zeros. And this example, I'm not sure, yeah. I think this one does give you a fourth color. Again, I expect this normally to be gold or silver, which is 5 or 10% respectively. But if it gives you a color, it's not going to be one of the odd ones. It's going to be, if it's yellow, and yellow is 4, it's 4%. But if you notice, there's a couple that aren't a straight number.
It's all.
Yeah, that's
1, 2, 3, 4, 5, 6.
Yeah. And I think the book is wrong.
the book's one.
I think so.
Do we have to know the tolerances out those percentages?
No, these that are odd percentages, I don't expect you to know. They will not, you won't be tested on those. It'll be a color, number, direct percentage for number. So if you get a brown, which is 1, it's 1%, red 2%. You won't get any odd ones.
That's why.
And there's only
Take it out,
two
they
values.
go-
Except
Okay,
just
green.
consecutive to 5, and then 2 other values, 25 to 1, and then no values for 89.
Yeah,
You got the rest of the side. Yeah, this is-
I can look it up. I mean, I can look it up pretty quick. Let me look real quick, because I bet you it's the book that's wrong.
Color code columns.
See, there's one right there. So it shows green, blue, and violet. So the book is wrong.
It's usually wrong.
The internet is, everything you read on the internet is true. The book is wrong.
The orange and yellow.
Yeah, it's
Okay, so like I said, it'll be a direct, you won't be using the fun ones. So in that example, it's red, green, red, red. Red is 2, green is 5. So we still have the multiplier, the third band is being 2, which is 2 zeros. And in that instance, it's not gold or silver, but red, so we're gonna call that 2%. 2%. Two resistors are connected in parallel. What are the resistance? Both are so many ohms. What's the resistance total? I think they're the same value, but it shouldn't matter. You should be able to get me a total resistance for two resistors in parallel.
So 1 over 1 over plus.
Parallel is 1 over x, x over 1, whichever.
Okay.
Two resistors are connected in parallel, both, okay, that was that one.
There you go.
Okay, so three resistors are connected in parallel to a 9-volt line. So you know right away, they're parallel, so they all see 9 volts. Total current is 6 milliamps. Resistor R1 is 1500. I don't know what the R2
It's just like being given the mesh.
R2 is 2500 ohms and R3 is something else. So you can do the current for each of those.
Yeah.
You can take the voltage and get the current with the 15 ohm, and then take the 9 volts and get the current with the 25 ohm. I think that's probably the only way you'll be able to do it, if I'm looking at this right. Yeah. You get the two currents, those are your 3 paths, and you subtract those the 15K current and the 25K current from, you add them together and subtract them from 6 milliamps, or whatever amperage is there. Is anyone not clear on that? I don't know how to explain it well. But that's my river scenario, and I don't want to go back to it.
Okay, 15,000.
It's 15, in this example, it's 15K, so I'll get a current using 9 volts. And then I'll use the 9 volts and I'll get the current for the 25K. And I'll combine the two currents and subtract it from the total current, and that'll give me my remaining missing current.
Okay.
Then you get a parallel, and it looks like it's asking for the resistance for, or is this, no, this is the one.
That's it right there.
Yeah, this is just the one we just did. So if they want the resistor, they're asking for a resistor R3, so actually I was thinking current for, so you'll have current for R3 if you do it the way we discussed. And then you can take the 9 volts, the volts divided by current to get resistance. So you'll take that 9 volts again, and then the current for whatever you got for the missing current, and you'll get the remaining resistance.
You'll subtract point oh six, like you said, from the material difference, you get the last current.
You get the last
You can
current.
find the resistance off the 9 volt.
You're given the total current, you figure these currents, you subtract these two from the total current, which gives you R3's current. You take the 9 volts divided by R3's current, and now you've got R3's resistance.
Can we just memorize the 1500 ohms as well? For the test?
You can do whatever you want. I mean, it's your test. You'll have no bearing on everyone else. They're right behind me on this too. Whatever the heck you want. Just put your name on it. Okay, a circuit consists of 3 resistors connected in parallel. A 10, a 30, and a 15. If the current flow through R2 is 3 amps, what's the voltage across R3? Okay, so they're giving you R3. They're giving you R3's current. Is that what they did?
Oh,
The
so
current flow through R2 is 3 amps. So they're giving us R2's,
So you get the voltage,
so you get a voltage.
then the voltage is the same.
And it's parallel, so they all see the same voltage.
He's getting,
You can do a grid on this if you want. You
Where
get
is
all the information you have. You fill out as much as you can on the grid with the information you have. And
Where's the voltage now? I mean,
where is the voltage?
it's not telling you the voltage on there.
Okay, when you have R2 is 3 amps and R2 is 30 ohms,
that's the, it's the same volt all the way across.
current and resistance will give you volts. It's a parallel circuit. 3
Oh,
resistors.
I'm sorry. Yeah, I did that.
No, I mean, this is
For some-
repetition.
I was thinking for some reason it was in ohms, not amps, so that's why I.
Yeah, they gave us all the ohms, and they gave us amperage for one of them.
Right.
And then we figure the voltage drop for one resistor, we know them all.
Right.
30 times
This is what this is doing is getting you to remember that parallel, they're all the same. That's really all this is doing. It's trying to get in your head that parallel circuits are all the same voltage. So they're asking you different ways, so you have to key and remember those things. Get the total voltages for R2, voltage drop is the same in a parallel circuit. Okay, 48 volt source is required to furnish 192 amps to a parallel circuit, consisting of 4 resistors of equal value. What's the value of each resistor? Okay, this is the one I said you can do backwards. You take the 48 volts and your 192 watts and you get a total resistance. You take that resistance total and you go into your calculator, you put in that resistance, you put in the total resistance and you do 1 over x equals. And that's going to give you a decimal. You divide that by 4 and you'll get a decimal and you do 1 over x again. Now, okay, so there are 4 resistors. So R1, what is it? R1?
What is the value of each resistor, meaning the resistance of each resistor, or what value is it looking for?
Okay, let's look at the same problem the way we normally been looking at problems. We got resistor 1, 1 over x plus 1 over x plus 1 over x plus 1 over x gives us a resistance total. When we do that 1 over x, it gives us a decimal, for each of these. And then we do plus, 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 and it gives us another decimal, something like that. So this decimal plus that decimal plus that decimal plus that decimal equals this decimal. When they give you the resistance total, you do the 1 over x just for the resistance total, and you get this number first. Then you divide it by 4, and you invert it again. And you've got these. They're all the same resistance value. So you just take your resistance total, 1 over x. If you want to try it, do like 45,000 ohms, 1 over x, and then you get a decimal. divide that decimal by 4, you get another decimal, you invert that again, and you're gonna get an ohms value. And if you wanna test your answer, suppose resistance total is, let's do this, 45,000. Somebody give me, just punch in 45,000 1 over x. Tell me what you get.
You get 0.0000222222.
4 zeros.
Okay.
4 zeros.
So now don't hit erase or anything, just put divide by 4.
Okay.
And tell me what you get.
Well,
5 zeros and a bunch of 5s.
0, 0, 0, 5 zeros.
Yeah, and the number 5. Out.
556.
Okay. Now don't touch anything. Leave that in there and hit x over 1 equals.
After you divide by 4, right?
After you divide by 4, you got this 0.0005.
Now x.
While that's still displayed,
180,000.
And that's total current?
180.
That's resistance. Total resistance.
Okay, 180,000.
Wait, we had the resistance. Total resistance.
And then you divide that by 4, right?
No.
180,000.
No, when you took 45K and you did 1 over x, you got 0.00022222.
Missing a 0 in there.
You divided, this one had 4 zeros?
4 zeros.
Okay. When you divided that by 4, that's when you get, see, we did this in reverse. We do resistance 1 over x plus 1 over x plus 1 over x, and we get a decimal and we invert it. But now we're just doing the exact same thing in reverse. We're taking the answer, inverting it, and dividing that by 4 to get this 0.00005. We invert that again, and we got 180,000. If you want to test that theory, take the 180,000 plus x over 1 plus 180,000 plus 180,000 x over 1 x over 1. Do that 4 times, hit equals, and you should get that decimal.
You keep saying x over 1, but it's
1 over x. Sorry, 1 over x.
Okay. Should that be written up there, 1 over R1 plus?
So this should be inverted?
Yeah, that's all I'm asking.
Yeah.
Okay,
I didn't learn any of this stuff till I got in here.
all right, that's fine.
I just
Oh, we
figured
get it,
turn
we
the
get it, we
wrench,
get it.
that's what I did.
All right,
That's
that's fine, I just wanna make sure.
No, I appreciate it, because like I said, I used
Well,
to
because
just,
you said we're doing everything backwards, so. oh,
Yeah,
is
no,
he-
I'm
is he
sorry.
flipping the numbers too?
no, sorry.
So, does that only work that inverse when all the resistors are equal? Or do you do extra?
Well, yeah, since yes, since they're equal.
All right.
Anyone lost on this? That's the key. I mean, if it gave you different, they'd have to give you more information if the resistors were different.
And I'm wondering how you got a 45,000. This question says you got a
Well, no, he
48.
did. That's
I
what
just
he
made
said.
the 45,000 up in my
Okay,
head.
okay.
It has nothing to do, you couldn't get anything on that.
I thought we were still working.
Well, we could do it. What's total resistance up here? Let's do it again with these values. 12 ohms? Okay, so with this one, we'll do this one, and I probably should have done that rather than increase the confusion. So 12 ohms,
Divide
1 over x,
1 over x.
and you get a decimal.
Yep.
What's the decimal?
0.0833.
Don't hit clear on any of these.
Now,
Okay, so that
divide by
you should have 0.0833 in the window and hit divide by 4.
4.
And give me that value.
0.0208.
Okay,
No.
now leaving that in the window, x over 1 equals 1 over x equals
48.
48.
48 ohms. Now, if you want to test it, do 48 1 over x plus 48 1 over x plus 48 plus 1 over x and a 4th time, and you will get 0.083. So that one is fairly simple, and I think, I don't know, probably made it tougher than it had to be. And you'll find you can do that a lot of ways. I've done it. Once you convert the resistance to that decimal with the 1 over x, it's regular addition subtraction after that. And then once whatever you can use the decimal values any way you want. And then when you convert it back again, then you get a legitimate number. Okay, so here's another. You have a parallel circuit with 3 resistors, a 10, a 20, and a 40. You measure 25 volts across the 40 ohm resistor. What's the current flow through the 10 ohm? So we know the voltage right away. We know the voltage for the 10 ohm, right?
Yep.
Because they're all 25 volts.
25 volts.
And you're after
Well, current.
current. So
So it's just.
voltage divided by the 10 ohms.
10 ohms.
Everyone got that one?
I know if I remember what movie, what series.
Okay, moving on. You have a series parallel circuit. This is worded word for word, except I changed the values. You have a series parallel circuit. 2 resistors are in series with a parallel leg containing 3 resistors of equal value. If the series resistors are both 125 and the total resistance for the parallel leg is 45, what's the total resistance? So they're giving you, it's kind of silly that they even tell you 3 resistors of equal value when they give you the resistance total. The parallel leg is 45 ohms in my example. So you don't have to even do any math. They're already telling you the total resistance for the parallel part.
You said the 45.
So then you've got 2 resistors above that are 125 each, 250. So it's 45 plus 250, and it's your resistance total. And then you get one of these. So you'll have milliwatts out for the total near the power supply. Here are your 2 currents. You've got these 2 currents. You take those 2 currents, you've got all your currents right off the bat. These 3 will share the same current because they're in series. You add this path, and you've got your front and back totals. Now you've got, we did that earlier, now you've got 90% of the information you need. You get your voltage drops in there, and you can start finding the missing voltages. Okay, what is the point of a Darson-Ball type galvanometer attached to? A small pivoting coil. And you can just say that. I mean, if that's all you say, you know, I know what you're talking about. Describing the basic operation of a galvanometer. Okay, they say galvanometer, and they're really just talking about the needle magnet assembly. So you've got current flowing through the coil, which creates a magnetic field, which attempts to align with the permanent magnets. And I say attempts because it's fighting a spring. Otherwise, it would just flop, and it would you put the least amount of voltage, and it would just center because it wouldn't have any resistance. So that's the purpose of the spring. You keep creating a balance. Describe the basic. Oh, there it is. Electric current passes through the coil, tends to turn its direction parallel to the lines of induction. The amount of travel is dependent upon the strength of the current, and the strength of the current is relative to that spring that it's balancing out against. And that's the whole test.